Example 1, we have this cube root of 27 minus x cubed. And looking at this, we want to find zeros, asymptotes, local min and maxes. So we're going to need a derivative. So the domain of this is going to be all real numbers because we can put any number into that expression. We can cube root negatives. If we look for a zero, we can see that the zero occurs at x equals positive 3. So I put that in my table of values. I put that on the graph. And just taking a look at this, you might be able to notice that there is a convenient coordinate. When x is 0, you can cube root 27. So when x is 0, we have the y-intercept is going to be at 0 and 3. Okay, and so I'm just going to put that in as well. So we'll put 0 and 3 as my y-intercept position. And we're going to then look at endpoint behavior. So what's happening? This is a, a, a curious one because what's happening as x goes to infinity? Well, essentially, if we take a look at this expression, this 27 becomes insignificant at both positive and negative infinity. And we're going to just end up with a cube root of negative x cubed. Well, the negative is going to come outside, and so we're going to end up with negative, but the cube root of x cubed is just going to end up being negative x. And that's going to be the same for both of these. So we're going to end up with y equals negative x as our limit. So as our endpoint behavior, so this is not what's happening locally, but what's happening as we get to extreme values, what's going to happen is this graph is going to behave like the y equals negative x function. So it's going to be the diagonal line with negative slope of 1. So although doesn't tell us, this endpoint behavior doesn't tell us what's happening locally, it's at these points here, but as we go off to infinity, this graph is going to behave like this diagonal line. So this is going to be, we're going to end up with an asymptote along that diagonal line. Okay, so let's take a look at the derivative and see what's going on with the derivative. As I differentiate this, this is going to equal 1 over 3, 27 minus x cubed to the power negative 2 over 3. And then we have to multiply by the inside derivative of negative x cubed. So we get negative 3x squared. So simplifying this expression, these negatives cancel out. That power is going to go in the denominator. Okay, so we end up with negative on top. It looks like the x squared is going to end up on top. And in the denominator, we're going to end up with this expression, 27 minus x cubed over 2/3. Okay, so the denominator is not defined at x equals 3, so we have a restriction there. And this is equal to 0 at x equals 0. So we have a horizontal tangent at x equals 0 and an undefined slope at x equals 3. So I'm just going to put that in. So at x equals 0, we have a horizontal slope. And at x equals 3, we have an undefined slope. Okay, so I'm going to write here, x not equal to positive 3, because that's going to give us a 0. Now this we have to be a bit careful of here, because this is, in this case here, there is a point defined at 3. In fact, we have that point on the graph. And in this case, we're going to divide by 0. So we're going to end up with a horizontal tangent, a vertical tangent at x equals 3. So this is not an asymptote. Okay, this is because the point is defined, the original coordinate is defined in this expression at x equals 3, but the derivative is undefined At that point, in this case, we get a vertical tangent. So this is going to be an infinite tangent. Okay, and if we did a limit from both sides, the limit of this is going to be negative infinity. Okay, so the slope is going to be negative infinity at x equals 3. So again, I'm going to label here, this is a vertical tangent. Okay, so drawing in that, I'm just going to draw that in. So we end up with a vertical tangent through that point. Okay, so this is, again, this is not, actually maybe I shouldn't draw it as a, this is not an asymptote, so I'm not going to draw it in like that. Okay, so I'm just going to draw in a solid line indicating a vertical tangent line at that point. Okay, so what we can do then is we can actually kind of graph this if we want. What this graph is going to look like, we have our, in fact, I should check my slopes first. So I'm going to do my slope chart, so f prime, and let's choose f prime at -1. Plugging that in, we can see that the denominator is always positive because of the even power. And then we always have negative in the numerator, so it's going to have negative slope through here. Okay, that's going to be horizontal slope. In fact, this slope is negative throughout. Okay, so at 0, we have our horizontal tangent. At 1, it's going to be negative, so we know it's going to be a slide through there. Okay, we have no negative slope. And then at x equals 4, again, it's just going to stay negative. It's entirely negative slope. Okay, so it's going to go vertical, and then it's going to go negative again. So when I sketch in this graph, the graph is going to look like this. It's going to follow the tangent line, sorry, the asymptote. We're going to have a horizontal tangent. I should draw this a little bit better. It's going to follow this line. It's going to have a horizontal tangent through here. And then it's going to have a vertical tangent through that point. And then it's going to follow the asymptote. So we get a graph that looks like this. So we're going to do a second derivative, but this graph we could have done without a second derivative. We're going to do a second derivative anyways, just to complete this analysis.